So I think we've waited enough. People are now online and in the room. Today we have two seminars. The first one is given by Kantor Tamaku, who is a PhD student in the Mechanical and Aerospace Engineering Department, and his work is based here at the Center for Automotive Research. And Kantor is co-advised by myself and Dr. Manfredi Villani, and his mission, alongside with Dr. Villani, has been to develop a fuel cell test lab. And for those of you who are interested, I am sure that at the end of the seminar, if you want to take a walk with him, he will show you the lab. But you'll see pictures of it. Then I'll introduce Michael later. I'm yours.
Hello everyone, my name is Kontan Hamadun. I am a PRA at CAR and MAE. I'm working with Professor Rissotti and Dr. Manfredi with fuel cell, and with this, one of these last session of CAR seminar of this semester. I'm going to talk about the development of a fuel cell test lab at the CAR. So basically in this presentation, I'm going to share a story of how tackling this. It seemed not so difficult to build a lab, but we've been working on it maybe for a year now. Let's briefly recap what fuel cell is and why we choose to study on it. And let's talk about some challenge and requirements, testing method, health indicators, and what we plan to do for the test and the components we have and what we expect to observe from this lab once it finished. Fuel cell, as you know, it is the energy conversion device that converts chemical energy from oxygen and hydrogen into the electrical energy. It has quite high efficiency. It's clean because it has no combustion. It has just only electrochemical reactions. It can be categorized by many criteria, but mostly we talk about the types of the membrane of the cell itself. We are focusing on the proton exchange membrane fuel cell, or PEMFC, because it operates at not so high temperature. We're talking about like 60 to 90 degrees Celsius. It has fast transient response and it has high energy density, which take less of the space, and we can stack up for more power requirements if we want, and that makes PEM fuel cell is widely used in automotive application. But you may say, okay, for the passenger vehicle at this moment, nothing really beats hybrid or battery electric vehicle because in terms of efficiency and stuff. But in big vehicles like heavy duty vehicles, like bus, like trucks, they have some challenge. The large battery size could contribute more weight and also more energy consumption and longer charging time. So to go clean and environmental friendly with this kind of vehicles, operating these vehicles on battery and charging station may not be the best option, especially when these vehicles have a fixed route to go and they have their own middle to run. Fuel cell can offer the middle ground with fast refueling, and it, of course, it has zero tailpipe emission. Hence, it makes fuel cell become more attractive to the heavy duty vehicle industry. But in the long run, the powertrain system of any kind of vehicle should still be able to achieve the similar task at its beginning of life. For example, imagine this like today, if you buy a gas car, right, you would expect it to run 20 miles per gallon on the day one today. And next 10 years on the day 3,650, you would still expect it to achieve 20 miles per gallon. So it's kind of same analogy for the fuel cell vehicles. So many organizations have proposed the operating hours requirements or service lifetime requirements to expect fuel cell vehicles should be able to achieve before it gets to its end of life or before it's becoming degraded. Let's say the loss of performance, fate. As you can see by the data from as you can see by the test data from the DOE on the fuel cell bus, its fuel economy decreased over aging. So by average, these organizations like U.S. Department of Energy, Japan's NATO, and Europe's Immortal Project, by average, these organizations aim for, let's say, about 30,000 hours of service lifetime of fuel cell vehicles. To test the durability and capability of these requirements, there are several test methods we can conduct for the fuel cell system. First is the long-term durability test. In this case, we would make fuel cell system operate at a certain condition over and over again for a long time to see the degradation. It could take up to 1,000 of hours to provide the insight of the actual lifespan and the degradation of fuel cell, but it might not be able to capture the effect of real world operating condition. Quicker ways to study this stuff is to do the accelerated stress test or AST. AST would regulate the stress factor such as high temperature or low relative humidity to stress fuel cells and reduce the test time. We can also do the driving cycle test. So you know that the driving cycle test, drive cycle is the speed or power versus time profile of the vehicle that can be used to represent the real world operating condition. But unfortunately, at this moment, there is no universal official test protocol yet. So there are just only some test protocol from different organizations. For example, this is the AST protocol for the membrane and the catalyst in the fuel cell from the organization named M2FCT or Million Mile Fuel Cell Truck, which is the multinational organization that they are now trying to push fuel cell system to be used in heavy duty vehicles. They combine the square wave load cycle like this with some stress factor such as high temperature condition here and low relative humidity to stress these components and study the degradation of the fuel cell. But what are they looking for, right? Before we get into the criteria of the state of health of the fuel cell, let's talk about the basic fuel cell characteristic. So in fuel cell here, hydrogen gas will be fed to the inlet of the anode side here, and only protons of hydrogen will be passed through the membrane here, and the electrons has to go to the external circuit here. So in this case, that's why we get the electrical current. And when they are passed to the cathode side, proton and electron will react with the oxygen that is fed onto the cathode side here and produce water. So the more electrical current fuel cell supplies could contribute to some voltage loss or overpotentials, which will decrease the voltage of the fuel cell due to the electrochemical reaction kinetics and resistance of the cell. So this behavior can represent by the polarization curve, which is the plot between the current or current density versus the fuel cell voltage. So as you can see, the more current you need, the lower voltage will drop, and multiply voltage and current, you will get a power curve like that. So there are several indicators to look as a criteria of the state of health of fuel cell. Again, at this moment, there is no universal agreement about what officially is the health index of the state of health of fuel cell. But researchers keep using these three stuff as a criteria to fuel cell health degradation criteria. The first one is the voltage or power. It is understandable that fuel cell voltage will decrease over time, which this can be observed by the polarization curve that we were just talking about in the last slide. This can come from, I mean, the degradation and voltage loss can come from membrane or catalyst or whatever components degraded. And the healthy cell should maintain higher voltage under the same operating condition, right? The second index is the impedance or resistance of the cell. So the electrochemical impedance spectroscopy or EIS method can tell us about how resistance or the impedance change over time, as well as the behavior of the dominance of overpotential in each operating point. And last but not least, we can see and compare by our eyes by doing the structural and morphological analysis techniques. We're talking about SEM, TEM, and XRD, but these are destructive methods. That means we have to cut and prepare a sample and put it into this equipment to see what really happens when the membrane of the fuel cell is degraded. So that means if we go this way, we cannot use the same cell to continue the test. It is difficult to compare apple to apple. So what are we going to do? To investigate this stuff, we plan to do aging test, maybe a mix in between AST and driving cycle, like what M2FCT does. And at the beginning of life of fuel cell and end of life, and after each aging session finished, we will try to diagnose and characterize the state of health of the cell. So at least we want to do polarization curve and EIS. And then this degradation behavior and these data sets will be used to create the degradation models as well as the development of diagnostic methods of fusion. So with that, these are the current state of what we are doing now. We choose to build our own lab rather than purchasing the whole test station because we think this would give us the capability and feasibility to scale up or down and have more, feasibility to do the test we want at this moment and some tests that we might want to do in the future. Let's starting with the stack itself. The main component, this stack is the 250 centimeter square with water cooling system. This stack can operate in the range of temperature of minus 25 degrees Celsius up to 90 degrees Celsius with 450 kilopascal of maximum reactant pressure. We select this side of active area because it's close to fuel cell size that is used in the real vehicles, comparing to other lab that it might be just only like 5 centimeters. The maximum capacity of the stack is about 1 kilowatts with 6 cells, but as a start, we will start to do the work with 1 cell first and expect to see somewhere around like 160, 170 watt per cell. Of course, fuel cell needs reactant gas, and feeding the reactants need to be accurate and require good mass flow controllers. We have calculated these reactant flow requirements for both hydrogen and air, but unfortunately, the mass flow controllers that we look in the market, they have either suitable for lower flow range, like for our 1 cell requirements, or specifically for the higher range, like flow rate requirement of our 6 cell. So there's no mass flow controller that could work entire range of our experiments. So as a start, we selected the mass flow controllers that can work with our 1 cell flow rate requirement first, and with help of Bill, now we have these mass flow controllers and gas line installed in our lab already. But later on, if we want to scale up the experiment, we would need another set of mass flow controllers to conduct the test in higher capacity. And the next thing is the humidifiers. Humidity is an important parameter that will affect cell performance. Humidifier is one of the most challenging components of our setup. Again, with our flow rate requirements, there's no humidifier in the market that can support our needs. So we had to build our own humidifiers. And there are several designs we could try. For example, the gas bubbling humidifiers or the spray chamber design. So we did some research and we calculate the amount of water that we need to keep our gas humidified for the gas bubbling type. We found some air tank for train horn, and we decided gas inlet and outlets, and also the gas and also inlet and outlet of the water. With LMAX, these are the gas bubbling humidifiers installed in our lab, and now it's waiting to test for its capability of humidification. Sales performance can also affect by reactant pressure. For the pressure, we will control by using the back pressure regulators with the pressure pilot control. The reference pressure from the pressure pilot control here will push the diaphragm in the regulator to control the required pressure. What we need to do is to feed the gas through the pilot control and send the analog signal to control the pressure. As of now, we need to complete our gas line to test this system. And for the temperature, which is of course another important parameter of the fuel cell system, we have thermocouples placed in different locations, which will allow us to measure and record temperature. At least we can read and record temperature in this spot, like coolant inlet and outlet, cathode and heat. And to do the electrical load. And for the DC electronic load, at this moment we have Fambro PLA 155K 6600. This equipment is capable of doing the polarization curve, but to do EIS, we might need other equipment to help us achieve EIS test capability, because this machine has no AC modulation capabilities to superimpose DC load and speed the frequency signal to measure the impedance test. And everything will go into LabVIEW. Every measurement and control will be read, measure, control, and record by LabVIEW. So we can log the data into the text or CSV file, and we can open this file with MATLAB or even Microsoft Excel to process the data and use that data to develop models. So once this lab is finished with this setup, we hope that we can use it to identify the degradation mechanism, evaluate operational condition, and generate reliable data, develop diagnostic method, and create models of fuel cell system and aging degradation models. So, like establishing fuel cell lab for degradation studies is a crucial step to improve fuel cell technology. The lab will contribute the valuable insight for both academic and industry application. And the findings of this work will help enhance the fuel cell durabilities and accelerate the adoption of hydrogen-based technologies. So as you can see, this is not an easy job, right? So if you see me walking around car or sitting in some corner and crying, feel free to give me some hug and share some love and support. Thank you for your attention.
Thank you. Very nice presentation, Connor. Excellent overview. Well done. Not only that, but even better done. Your timing was perfect. You left a few minutes for questions, just as we were hoping. Please. Also questions from the audience online.
Yes, sir.
Yes,
Slide 16. You show oxygen, the O2 flow rate.
Yes. sir.
Do you have to put pure oxygen into it?
Oh.
What's that for?
Well, actually, we were just air. So
Yeah.
we calculate.
Yeah, that's what I thought, yeah. So what's the oxygen for? This is up on the top left, this is O2 flow rate. On the top left, that chart. Why does it say O2?
At first, we have to calculate for O2 flow rate first.
Oh, you're calculating.
Yes.
You're not putting it in there.
no, it comes from the air.
Right. That's what I thought.
But I'll tell you, I'll add a comment if you don't mind. You've been around our seminars long enough that you may remember our land speed record of fuel cell vehicle from
Right.
many years ago. To maximize the power we could get from those fuel cell stacks, instead of using, first of all, a compressor to compress the air, which requires energy to power the compressor, we put the gas in a pressurized vessel, just like the hydrogen. So we put out all of the compressor and associated energy losses.
It's regular atmospheric gas.
Well, initially. But
Okay.
then we started asking questions. This was a project that lasted a few years. And it turns out that we started inquiring, how much oxygen can you actually have?
There you go.
And the answer was that you could go up to 40% oxygen without worrying about the oxygen being too oxidizing for everything else.
Right.
Because you go too high, I mean, you could say, well, what if I use pure oxygen? That is about as corrosive as it gets, okay? Oxygen is your friend when you breathe it in air, but it's at 20%. Anyways, so what we ended up doing was to actually you can buy industrial gases, pressurized bottles of helium oxygen with 60% helium, which is inert, okay, and very light, and 40% oxygen.
Mhm.
And that led to a significant increase in power output because now that would be double your oxygen flow rate. So,
Thank you.
good question. Yes.
So nice presentation, Conton. And like, I have a question on the end of life criteria for like, what is it like for the,
As of now, like, let's say we are focusing on the performance loss. Basically, we are focusing on voltage loss. The end of life of fuel cell is about when the performance decreased by 20%.
okay, so like few, similar to like
Kind of similar to battery,
battery,
10-20% losses.
but here it is power loss, but in like it in battery electric vehicles, it is the capacity loss that's 20%. It might not be like 20% in power loss. So why is it power loss was 20% here?
This thing is not energy storage. And the performance, it really depends on the electrochemical reaction on the basis. So that's why they are using the power loss instead of capacity loss.
Okay, so like, but 20% seems like a lot of power loss.
Yeah. 10-20%. So as I mentioned, there's no really like official criteria. So it's kind of ballpark that they play around.
Thank you.
More questions? In that case, bring on the rest of the troops. Thank you, Contra. Well done. Would say that was a really successful presentation. This is Contor's first presentation, so we wanted to make sure. Well done. Excellent. So Michael Nye is, on the other hand, is a graduate student, a PhD student in the Department of Electrical and Computer Engineering, and he is co-advised, to the best of my knowledge, by Dr. Matilda Derpino and Dr. Julia Zhang, who is an associate professor in electrical and computer engineering, and who is the queen of electric machines at Ohio State. Dr. Derpino is maybe the princess of electric machines at Ohio State. So Michael, he'll tell us what he's doing, but, his expertise and his, research work are in the world of, electric machines. And I have to ask you a question. Any relationship to Bill Nye?
Not that we know.
Not that you know of. I have to tell you that, for those of you who may not know, who Bill Nye the Science Guy, if you don't know, look it up, Bill Nye the Science Guy. I met him in person. When I came, this was many, many years ago, brought home to the kids, the program and this event I was with Bill Nye's signature, I became God for a couple of days. You get that. Anyways, if you don't know who Bill Nye the Science Guy is, go do a little internet search.
He had a TV show.
Oh, you bet he did.
Yeah.
It was awesome. All yours, Michael.
Thank you, Dr. Rosati.
Yes, we.
You need to do some sharing or?
Yeah, please.
Oh, he isn't a presenter.
Cool. Sorry about that. Anyways, thank you for the introduction, Dr. Zoni. As he said, my name is Michael Nye. Here at CAR, I work with Dr. Matilda Garpino, and I also work at the Center of High Performance Power Electronics, aka CHIPPE, with Dr. Julia Zhang over on main campus. So that's usually where I spend most of my time, but you may see me between here and there a lot. Today, we're going to talk about permanent magnet synchronous machine core loss comparisons between both empirical and numerical approximation models, which is a mouthful, as I'm sure you can tell. Agenda is pretty straightforward. We're going to go through an introduction, probably going to be pretty math heavy, so I might kind of fast forward because I don't know for everyone. And then some of the methodology on the conclusion. So the introduction is we like our electric machines to be as efficient as possible for all applications. Primarily, we looked at electric vehicles, but in general, obviously, better, more efficient is better. And it's impossible for a machine to run at its most efficient state if you don't know what all of your losses are, or if you at least don't calculate them. Unfortunately, for electric machines, you have mechanical, electrical, and magnetic losses. Correct me if I'm wrong, I believe mechanical losses are generally relatively easy to compute. Some of the electrical losses for the DC component for the ohmic loss is pretty easy. It's your standard I²R formula, but your magnetic losses become quickly incredibly complicated in that they're very geometry dependent. They're material dependent. They involve three-dimensional physics over triple integrals. They are not fun to compute. Even with, you can use basic lumped models for your magnetic reference of the machine, but those usually don't give you very accurate losses for the magnetic state. So you generally need to use a lot of finite element analysis or other computationally heavy strategies to get good core loss approximation. But those are very time intensive and computationally intensive. So it is generally beneficial to have at least an approximation framework that can get you relatively close to what your expected loss is when trying to get your machine to perform efficient. So we are working on basing this work off some papers by P.H. Miller et al., which they talk about how to frame the approximation using the direct currents of the machine, which are relatively easy to obtain. We only expanded it into the entire left-hand plane or left-hand region of the DQ plane in the second and third quadrants. rather than only a few specific points like the other examples of this framework have. So under the methodology, we're going to start basic and work our way up with the Bernoulli equation. So the Bernoulli equation is a pretty standard method of calculating the core loss of an electric machine. This is one form of it. There are a couple of them. Some don't include that third term for excess loss. Some change the coefficient on F and B in the hysteresis loss term. But basically, it breaks up the loss into three types. There's hysteresis, which is linear. There's the eddy current loss, which is squared. And then there's the excess loss, which is to the 1.5 power.
And those are scalar B's, it's just a peak value.
Yes, so F is the electrical frequency of the system, B is the peak magnetic flux, so as we said, they're scalars, and then KH, KED, and KEX are the fitted coefficients of hysteresis, eddy current, and excess loss components. Using FEA, this can be broken up into, lots and lots of elements based on your meshing, and it solves the equation for every single element. Obviously, this is better than a lumped model, but it quickly becomes, again, computationally and time intensive if you're trying to generalize to a whole region. So what Mellor suggests is breaking this up into two different versions, which are going to be based on the open and short circuit conditions of the system. The logic is that based on the right, all of the magnetic flux can be seen as a superposition of two states, and those two states are the open and short circuit. In the open circuit, all of the flux paths generated by the permanent magnets travel through the back iron and around the windings, which induce a voltage in the windings, no current. In the open circuit, on that right image, the idea is that the current generated perfectly counteracts the flux that would be generated by the magnets. And now the magnetic flux paths do not go through the back iron and around the windings. Dr. Zone was confused, but do not go through the back iron and induce voltage in the windings. They instead go through the stator slots. So in theory, under this assumption, any operating condition, the magnetic flux should be able to be seen as a superposition of the open and short circuit. And based on this, for any open and short circuit condition, that scalar B that we talked about in the previous slide is a constant and can be lumped in with the fitted coefficients for the open and short circuit conditions. So now our two equations that we're going to use have two sets of different fitted coefficients.
They say your presentation stuck on the first page.
You may have to exit and re-enter. Literally, yeah. And unshare and reshare. That's probably when that happens, the only way you can make it work. Sorry about that.
No, you're good. I feel like I'm just going to do this and it's going to go back to the same issue. It probably got stuck here, I'm guessing. This is going to view this as a different screen.
Still stuck at
Yeah.
Well, in the worst case, you can exit presentation mode. It won't be as big, the picture won't be as big, but your images are clear and your text is large, so you can get away with not being in presentation. Worst case.
That's that.
That should
Can you
try to move now.
Cool.
Yeah, good. Awesome. Thank you.
Cool. Sorry for all of that.
Good now, says Matt. Good.
Okay. Back to it. So, based on these two previous equations, the electrical frequency of an electric machine can be related to the induced voltage by the flux linkage of the system. So that equation is F equals V over lambda, where lambda is flux linkage. So we now reframe, instead of having the electrical frequency, or sorry, electrical frequency in the system, we reframe it with a magnetizing and demagnetizing voltage based on the open and short circuits. Those are the voltages that are induced in the open and short circuit cases. And lambda PM is the flux linkage of the permanent magnets of the machine. Our magnetizing and demagnetizing voltages, again, this slide just calculates what their magnitude are based on the vector diagram, the TQ reference frame of the electric machine. That's the vector diagram. So you get the different vectors based on the DQ currents of what axes the flux are on, and what the total voltages and currents are. I won't go super in depth on that diagram. Here's the general equation of what we find the magnetizing and demagnetizing fluxes to be as a function of fluxes on the D and Q axis currents, which are functions of the the fluxes on the D and Q axes, which are functions of the DQ axis currents. Lots of functions of other things in those. So the final claim based from Mellor is that the total core loss of the system can be seen as a superposition of the core loss of the open and short circuits. So you finally get that big long equation where all those V's are functions of lambdas, which are functions of ID and IQ. That is the claim, but in Mellor's work and the other work we found, nobody seemed to generalize that to the entire DQ frame and prove whether or not it worked for the entire region. They only proved or showed a few select points. And they, I believe, used a zero ID axis control, which works for surface permanent magnet machines, but not internal. Well, it works for internal permanent magnet machines. It is not the efficient strategy that you.
Zero ID means constant flux.
Yes. Yeah. So model. So in order to test this, we wanted to model a machine. To do that, we picked the permanent magnet synchronous machine of the Nissan Leaf. It's a pretty standard or common machine. The Nissan Leaf as a vehicle is relatively common in terms of EVs. It's been around for a while. We could find most of the parameters of the machine. So that is a cross section of a segment of the designed machine. It looks like any other IPM cutout you might see. But that is what we need for an FEA model using ANSYS Maxwell 2D. Here are the parameters. We tried to keep most of these testing parameters as closely as we could to the actual Nissan Leaf. Unfortunately, because we weren't able to get every single parameter of the Nissan Leaf exactly, as well as the electrical parameter, like the parameters of the electrical steel, we did have to change some of the numbers slightly. So the DC bus voltage is the same, the max rotor speed, max torque, those are the same. Max power is slightly different, and we had to estimate the phase resistance based on the winding dimensions. The big change is the peak phase current is half that of the Nissan Leaf. We have it in order to get all of the other numbers to match. We worked around with having the stack length and changing a couple other things. This seems to be the easiest solution, was to just have or limit the total current of the machine. But other than that, all of the numbers should match between our FEA model and the true Nissan. Then here's the the torque speed curve of the generated FEA model. On the left, here's the efficiency map. This is generally what you would expect for most permanent magnet synchronous machines. On the right, we have the output power. Again, as you get further towards the maximum part of the curve, you get higher output power, which again is as for what we would expect of this machine. And then to verify the theory of the magnetic flux paths, we ran FEA and open circuit. So on the left, we have the open circuit. Here you can see the magnetic paths travel from the North Pole magnet around the back iron to the South Pole magnet as predicted. And then in the open circuit case, They generally do not go through the back iron. It was difficult because we had to wait a long time in order for the system to reach mostly steady state. So you can see some of the flux paths do still go through the back iron, but generally they either go through the windings themselves or they travel through the bottom of the stator slots, which would not induce voltage in the building. So then using the open and short circuit data, we model our Bertotti fits of those two curves. So here we overlay what ANSYS says the core loss should be, and we find fit models to what that core loss is based on the Bertotti model. We tried for both the open and short circuit cases 2 different Bertotti models that did account for both the inclusion and exclusion of the excess loss term. The Bertotti model is hand wavy at best. It is definitely an approximation. The excess loss term generally is used to make it work slightly better, but the excess loss term also doesn't really have any physical principles as to why it should be there, other than to make the fit better. So we tried both an inclusion and exclusion of an excess loss term in order to kind of account for that. Regardless of the inclusion or exclusion of it, the fits are generally the same. And either way, you get an R squared of around 0.99 to match the fit data or the expected data from ANSYS. So it worked generally well either way. At the right, at the top, you see the fit coefficients for both the open and short circuit cases, with the inclusion and exclusion losses. Really, the only big difference between those 2 fit models is the short circuit case becomes more linear. I guess you could say the coefficient for the linear hysteresis is almost 3 times as large. But other than that, the coefficients generally don't change between the inclusion and exclusion of excess loss term. So we also tried to better account for saturation inductance rather than assume a lumped DQ axes inductances. In order to account for that, we created polynomial fits of what the fluxes are. That's something with ID and IQ. We tried several different fits. So here's all the different R squareds we got for different combinations of polynomial orders of ID and IQ. The green ones are the ones we went with for the D-axis flux and the Q-axis flux. We picked ones that had relatively high R squared while also trying to still minimize the complexity of the polynomial because we don't overfit and just make the model more complicated. So it ended up being second order for both ID and IQ for the D-axis flux, and it was third order IQ, first order ID, the Q-axis flux. So our results. So we ended up running over 2,500 simulations of ANSYS, which took a long time, all spaced out throughout the left-hand side of the DQ plane, second and third quadrants. Here was the spacing of our points. So 0 to 300 amps at steps of 20. The current angle was 90 to 270 at steps of 10. And we did rotor speed from 1,000 to 9,000 RPM. If you do that math, it ends up being like 2,700 simulations, but about 200 or so are cut out because of the repeated value of 0 amps at all angles is the same point. So we only ran that. So here's what we get. So on the right, we increased from 1,000 to 9,000 RPM, and those plots show what ANSYS says the core loss should be, as well as the predicted core loss with the Bertotti fits that we got. One being an inclusion of the excess loss term, one being an exclusion of the excess loss term. What we see is in all 3 cases, they generally have the same magnitude and generally have the same shape. The 2 approximation models are almost the exact same, which makes sense based on the previous slide. Those 2 curves were essentially the exact same, regardless of the inclusion or exclusion term or excess loss term. So superposition shouldn't really be affected by it. The third, with the excess loss term, The fits seem to be marginally better. So that's what the next couple slides will talk about. But in general, this approximation produces similar results as to what you would expect from this. This view is a little hard because it's top down and three-dimensional. So on the next slides, we have contour fits, which might be a little bit more easy to look at. These ones represent the absolute difference between the approximation model and the FEA model of the predicted core loss. The black line represents the MTPA curve, the maximum torque per amp curve, used for internal permanent magnet machines. It's typically a popular control strategy that is used. So this at least gives you a general region to consider of what points kind of matter the most that we would want to really plot what our core loss should be. So you can see that as we increase up to 9,000 RPM, the region gets smaller due to the increase of back EMF from the magnets. And the approximation, the absolute difference does tend to get worse as we get into higher and higher speeds. This makes sense somewhat because the magnitude of the core loss is much more significant at higher speeds than it is lower speeds. At lower speeds, it's we're in the scale of tens of watts versus at higher speeds, we're in the kilowatt range. So 2 orders, 3 orders of magnitude difference.
But percentage wise, because at high speed you have more power too. So as a function of the power, the machine delivered power. Because losses in watts as a fraction of the power the machine is delivering.
So the maximum output power is 80 kilowatts, and the core loss at high speeds is in the kilowatt range. So 1 out of
Yeah.
82.
And if you're at low speed, what's the power output? You can't deliver 80 kilowatts at low speed.
Yeah, I would need to sit down and do that.
Yeah, so I think
So,
thinking of it as percentage of total power losses could be interesting.
That's a good way to frame it. We did frame it as a percent error, but just between the ANSYS model and the approximation, because like you just said, having a absolute difference is somewhat not helpful, kind of helpful. So we did also model it as a percent error. It would be interesting to see how it's a percent error relative to the maximum or like the total loss or the total power. But we did model it as a percent error. So here you can see that at low speeds, it's actually pretty bad because when even if you get a small difference of wattage, when you have 10 watts total of loss, that's a pretty significant margin of error. But at high speed, it's relatively condensed around plus minus 10%, I think, which is pretty good given the approximation model, especially when you start talking about the kilowatts range. So this polynomial approximation using all of that math at the beginning can give you a relatively good approximation of what ANSYS would take or what any other FEA models might take while being significantly fast, which is part of the conclusion. So the proposed approximation can generate core loss predictions of relative accuracy. As we did see, there were some minor errors, and I'm not saying our method is better than what ANSYS could get you because it is much dirtier and it's not taking the fine meshing, but at least gets you a relatively close order of magnitude of, core loss, which is much better than not calculating it at all. The proposed methodology also needs fewer FEA simulations to generate core loss. Getting the entire DQ plane with all those points, there were 2,500 simulations. In order to get this approximation to work, we needed about 20, and I could probably do it with less if my Bertotti bits were a little bit more rough. You only needed a couple for both the open and short circuit equations. And then finally, the proposed approximation is a polynomial function of the DQ currents. The DQ currents are relatively common to measure anyways for most control strategies for machines. So in order to take a polynomial of those, can be done either by hand, real-time control system, whatever you need without the necessity of large lookup tables in order to calculate. So That, there are my references. And the next one.
Thank you, Michael. Very nice presentation and also excellent timing in spite of the little glitch. So well done, both of you with and questions. Yeah,
I don't know if this applies, but analytically, the thermal conditions of the material, that would change the magnetic fields, the different temperatures of the material would.
Yeah, but to some degree,
Because you have to keep, when you do an actual test, you run the machine, do you maintain, how do you maintain the temperature of the metal to match your analytical predictions?
in my experience, I have not necessarily worried about the temperature of the metal. Most of our cooling is focused on the windings.
Right.
The windings are gonna generate a lot more heat due to the electrical currents. Obviously, by default, the steel.
So there's an operating temperature for the motor.
Hmm.
There's an operating temperature for the motor. You said they're cooled, the windings are cooled.
Hmm.
That's an operating temperature, isn't it?
I think one tries, how the electric machine is cooled.
Yeah.
Depends on how it's designed and for what application it's used. It could be liquid cooled, that's pretty expensive. In our Buckeye Bullet land speed record vehicles, we were using splash oil cooling. And that ended up being for that really for those high performance conditions, temperature was the ultimate limit. As far as how much power we could generate. Machines can be air cooled, so it really depends. How's the?
Analytically speaking, how do you put the temperature cooling system into your model?
This model does not account.
Doesn't account for it. Okay.
It's a good question, and I think that it is possible to incorporate those elements in a finite element analysis
Yeah.
too. You're just making it significantly more complicated, and instead of just designing the geometry of the windings and of the laminations and of the permanent magnet, you have to figure out where all the cooling passages are. It's complicated.
FNEs are, the cooling thing doesn't apply to FNEs. If you want to use an FNE to analyze your machine.
I think you could.
You
It
could.
just becomes a lot more
It
complicated.
would be more complicated.
And this is partially why the Bertati equation and other approximation models you see have this excess loss term. So these two are rooted somewhat
Okay,
in physics. The excess loss term makes it work.
thermal things.
Yeah. So I had another question. How much, I was presuming that the Nissan Leaf uses an interior permanent magnet machine with some asymmetry giving rise to reluctance torque. Does that matter? Does it change the fact that you may have, in addition to the permanent magnet torque, some reluctance torque? Does that figure into these calculations of losses? Because that changes the flux, right?
So that's why we model fluxes polynomials of the DQ currents. Because obviously flux is in some way synonymous to the inductance. Because normally you would assume that this is LD ID plus lambda, and that would be LQ IQ. And those would be your terms. So we model these as.
So it incorporates the possibility or that there is and then your finite element model would incorporate that. More questions? Very nice. And I suppose that very last question. What if you actually had a Nissan Leaf electric drive and it should be, I know you can put it on that monitor and do the measurements. So how accurately do you think you could measure these losses?
In terms of the specific hysteresis eddy current, probably not in my experience, do I know how to do that? Generally, the way that we would do it is we would take the input power.
You'd measure
minus
total
the output
losses.
power, and there's some loss there. And now, again, going back to what we said at the beginning with mechanical losses and the ohmic losses, ohmic losses are easy.
That's easy, right?
The mechanical losses, I can estimate with relative somewhat accuracy.
You could do some motoring tests. with that. In other words, have the motor off and just spin it, and you could get some estimate of the mechanical.
So that with some math could be done. And then you just assume the rest is
And the rest is,
loss. So there's gonna be some AC electrical losses due to skin effect and proximity effect, and that's a whole other difficult
Yeah.
math behind this.
but those percentages I suggested, I think that's a good idea.
Yeah,
To represent things as percentage of total power. Awesome. Michael, oh, yeah,
Yes, just one question, like, it's coming from Dr. Zoni's question, like, you said there are 3 types of losses, so like, what are the, like, I don't have much knowledge, but what is the proportion of these 3, like, in the total?
So that's gonna be a function of what speed you're at. At low speed, and I don't do a whole lot with the mechanical side of it, being an electrical engineer. Mechanical losses, you're looking at friction will increase with your rotor speed. I believe that's linear, yes, more or less.
yeah, and I think in general, I mean, think about it, friction losses are essentially journal bearing losses, right? And yeah, there is a little bit of aerodynamic drag, but it's pretty minimal, right? So I would say that the ohmic losses and the core losses are the dominant components.
And I would say that those switch from low to high speed, because low speed, you can get much bigger current. Which the I squared R is ohmic loss, so much bigger current squared is a lot bigger. Versus down here, your region is much smaller what you can actually use. And again, the core loss increases by probably 2 orders of magnitude between the low to high speeds.
Yeah, just a couple of questions relating the result. I have some experience with ANSYS. It was more relating to different topic, but it was interesting to find in the first experience that some result could change. Not so much, but depending on the size of the mesh, but also on the element type. So did you find the same experience for the flux?
So we did do higher resolution
Mhm.
models, which again took a lot more time to view.
Computational time will increase.
And we kind of hit a flat line of what that looked like, that the core loss progressively had less and less ripple, but it didn't really change because it's mostly a DC value, the
Yeah.
steady state, loss. That the ripples got smaller and we were able to get a finer value, but eventually we kind of hit flat. So, meshing and time steps and all.
Great, thank you.
Thank you. Thank you, everyone. More seminars coming in the future.